Yeah, you may start, Dinesh.
Yeah, go ahead, Madhuji.
So, hello everyone. Welcome to the third workshop of Commnet. So, this workshop will be basically about source coding, and we'll do some modulation and demodulation techniques and simulate them on MATLAB. So, this workshop, I'll conduct this workshop because Harin has some other engagements, so I'll be conducting this workshop. So, without further ado, let's move on. Source code. So, first we come to source coding. So what is basically source coding? Source coding is the process of assigning codes to symbols output by the source. So what does this basically means? Before transmitting the information, we are encoding them so that it can be transmitted efficient for more efficient transmission. So and for security reasons also. So that's basically source coding. And in addition, we compress it in order to get a representation with a minimum number of bits to increase the speed of transmission and memory requirements. So basically, that's the case, right? So we'll be trying to compress the data, right? So that the data can be transmitted more efficiently. It will require less space, and hence the speed of transmission will also increase. And we'll try to do that with the least loss possible in data. So that's basically the purpose of source coding. Here will mostly do the source coding in binary format. So let's look at some of the types. So some of the assumptions which we'll make before we will move on to source coding are we model the source as a system that generates random symbols. So the source will be a system that will generate random symbols for each data type, right? Data. Then the random numbers are modeled using probability. So suppose last time, as in previous workshop, I have mentioned the symbol which occurs more frequently, right? If we'll assign a longer bit sequence to it, then it will require more space in as compared to a case in which we assign maybe a smaller sequence. So that's so by observing the probability of occurrence of these symbols, we'll try to minimize the data that is required for transmission. So the source is using output symbols which has known probabilities. So that's basically some of the criteria which we'll take into consideration while we are discussing source coding. Moving on. So suppose we have a set of output symbols S1, S2, Sn, and each of them has a probability pi associated with Si. Suppose we have a set A, B, and C, and the output is basically A, B, C, C, C. So you can, it's obvious, right, that A occurs two times out of 6. So its probability will be 2 by 6. That is 1 by 3. B occurs once out of 6. So its probability 1 by 6. And C occurs 3 times in out of 6 times. So its probability will be half. So that's the probability of the symbols A, B, and C. Then how will this help in source coding? A code word. It is the binary representation of the symbol obtained after source coding. So what we are saying that the suppose for the symbol A will be appointed a binary representation for the symbol. Suppose here, as we have seen, suppose A, we are assigning 0, 0. So that is the binary representation of the symbol A. For B, it's 0, 1. So that is the binary representation of symbol B. Similarly, for C, it is 1, 0. So now we have seen that we have assigned a binary representation to each symbol. So how will you know that this code is more efficient than suppose I am assigning 0 to A, 1 to B, and 1 to C? How will I know that if this code is more efficient or if the other code is more efficient, right? So for that we have a parameter called the average length of the code word. So in this here we'll make use of the probability of occurrence. Average length will be the average length of the coding scheme is the weighted average value of the length of the code words, which is basically saying that it is a summation Am I audible now? Can anyone confirm?
Yes,
Yes, we
Amik.
are.
हाँ, ठीक है. So that's basically it. We are multiplying the probability with the average length. So here in this case is easy, right? Because all of them have the same length, 2. So A has the probability of 1 by 3. So 2 times 1 by 3. Then B also had a length 2 plus 2 times and the probability of 1 by 6. 2 times 1 by 6. And C had a probability of 1 half and multiplying it by 2. So in that summation will be 2. So that is the average length. So that's so the basic why we're so the main purpose of the compression. How will you know that the compression is better? So as the average code length of the coding scheme will decrease, will so it will definitely be more efficient, right? So this is the parameter for checking the efficiency of the compression. So that's it. So this is the average length of the coding scheme that I have mentioned. So it's 2, right? So suppose we are taking another coding scheme where A is 1, B is 0, 1, and C is 0. So the probability of A is 1 by 3, right? And the length of the code word is 1. So 1 into 1 by 3. For B, its probability is 1 by 6 and its length is 2. So twice of 1 by 6. And again for C, its length is 1 and its probability is half. So in this case, we get the average length to be 7 by 6. So obviously 7 by 6 is smaller than 2, right? So the average length of the code words which is being transmitted is 7 by 6, which is better as it is less, right? So lesser it will be better as this that means there is better compression being done. So the second scheme is obviously better. So next, moving on. Uh, what are some specific special types of codes? First is the non-singular codes. So while transmission, the for a non-singular code, all the codes for each symbol will be different. As we can see in the previous slide, suppose A had a code 00, B had 01, and C had 10. So we can see for each of them it is different, right? So that means it is a non-singular code. For each symbol, there is a different code. But suppose A had also a 0 and B was also represented by 0. So that is a singular code, as the code for all symbols are different. Next, moving on, uniquely decodable code. In uniquely decodable code, there is only one specific possible way of decoding that. So suppose some sequences we can decode them in one or more than one ways, right? So for uniquely decodable codes, that is not possible. Suppose here we are considering a symbols A, B, and C, and which have the codes A has 0, B has 1, and C has 0, 1 respectively. Suppose for the we have to decode the sequence 0011, right? So how many there will be many ways in which this can be decoded. Suppose the suppose it is AABB, right? A is represented by 0. Again, it will be 0. Again, it will be 1. Again, it will be 1. So ABB is one of the possible decoding sequence. One of the possible decoding sequences for 0011. Similarly, we can see that suppose the first bit represents A 0, then the next two bit we have is 0 1, that can be C, and the next bit is 1, that is B. So ACB is one of the possible decoding sequences which you can get. So we can obviously see that there is not one single way of decoding this, right? So there will be multiple phrases which can be decoded from this sequence. So hence it is not uniquely decodable. We'll see about one examples of uniquely decodable codes in the next slides. Next, instantaneous codes. Instantaneous codes are are a subset of the uniquely decodable codes, which we don't need to know about the subsequent bits to decode the sequence of the current bit. So, so this might confuse you a bit. I have an example table which I'll show you how it is done. Then a prefix code. Suppose we have a prefix of a code word C1, C2, C3, Cn. So in the prefix code, no sequence is a prefix of another sequence. Suppose here we have an example: A is 0, B is 0, 1, and C is 1. So we can see that A is the code word for A is a prefix of B, right? Because 0 comes before in the sequence 0, 1. So A is in the sequence, the code word for A is in the sequence of the code word for B. So this is not a prefix code, right? Because A is the prefix of B. 0 comes in 0, 1. But in the next sequence, suppose A is represented by 1, 1, B is 1, 0, and C is 0. This is a prefix code because no, as suppose for A, 1, 1. 1, 1 does not come in any of the, as a prefix in any of the code words for the other symbols. So 1, 1 does not come as a prefix in B, which is 1, 0, right? Similarly for B and C. So hence it is a prefix code. Means you means no symbol is a prefix of another symbol. So this table will make you easier to understand. Suppose first we'll discuss about code 1. In code 1, symbol A has a code word 0, B has 1, C has 0, 0, and D has 0, 1. So is it a non-singular? Yes, because each symbol has a unique code word, right? A is represented by 0, B is represented by 1, C is represented by 0, 0, and D is represented by 0, 1. So for each code, it has a unique code word. So both A and B are not represented by 0 or something like that. So it is a non-singular code. Is it uniquely decodable? No. Why no? Because as you can see, suppose we have a sequence 0, 0, 1, right? So what can the possible decoding sequence be? Suppose we have 0, 0, 1, right? So it can be AAB. A is 0 and B is 1. So it can be 0, 0, 1. I'll often use whiteboard for this. So it will be easy. Is the whiteboard visible? Can anyone confirm?
Yeah.
So we have A, B, C, D. A has 0, 1, 0, 0, and 0, 1. Pardon my handwriting, but it's quite difficult to write on a whiteboard. So suppose we have this sequence 0, 0, 1. So what can be the possible decodings? Uh, First one, it can be AAB, right? Because A is 0, then again A is again 0, and again B is 1. So that is one possible decoding sequence, right? Next, what can another sequence be? Uh, C, it is also one possible sequence, right? Because C is 0, 0, and B is 1. Again, another possible, what can be another possible sequence? It can be A, B. Why? Because A is 0, and again D is 0, 1. So we can see that for a sequence, there can be three different ways in which it can be decoded. So it is not an uniquely decodable code, right? Hence, this sequence is not uniquely decodable. this code for A is where A is 0, B is 1, C is 0, 0, and D is 0, 1. Next, suppose we have A, B, C, D, and for which the code words are zeros, 0, 0, 0, 1, 0, 0, 0, 1, 1, 1, 0, and 1, 1. Is it a singular code? Yes, because each of them have a different code word, right? A is represented by 0, 0, B is 0, 1. So each of them is unique. So it is a singular code. Next, is it uniquely decodable? Yes. Why? Let me show you an example. Suppose we have this sequence 0, 0, 0, 1, 1, 1, 0, 1, 0, 1, 1. So, for the first two bit words 0, 0, what can be the only possible outcome? A, right? Next, 0, 0, which gives to A. Next, what is the next two code words? 0, 1. What will that be? It will be B. Then, what is the next two code words? 1, 0. What is it? It is C. Again, what is the next code word? 1, 0, which is again C. And what is the next code word? 1, 1, which is again D. So you can see that there is only one possible way of decoding this, right? Yeah, so if we start from the beginning, there is no other way in which you can decode. So we'll only get this sequence A, B, C, C, D. So hence it is a uniquely decodable code for this. For this, it is a uniquely decodable code. It is also a singular code. Uh, Next, is it instantaneous? So what was the definition of instantaneous basically? Instantaneous codes in which we don't need to know about the subsequent bits to decode it, right? So suppose we have one code word, the first code word. We have received the first code word, suppose 0, 0. So do we need to know what the next bit will be to decode it? We don't, right? Because 0, 0, it can only be A. Again, we receive the next code word, which is 0, 1. So do we need to know the next bits to deduce whether 0, 1 represents B or C? No, right? It obviously represents only B. So similarly, we can go for 1, 0, 1, 0, and again 1, 1. So you can see that there is no, so we don't need to know any subsequent bit. We don't need to know the next bits of 1, 0 here, suppose, to find out whether it is a C or a D. Hence, it is a instantaneous code. So that is basically the definition of instantaneous code. So, but but in this code here, 001, we cannot say anything about whether whether it is yeah, the next whether it is a or a C without knowing the next bit, right? Because here the first bit is 0. So what can it be? It can be first we have received a code word bit B, 0. So it can be A, but it can also be C, right? Because without knowing the next bit, we cannot actually know anything. So hence it is not an instantaneous code. Without knowing the subsequent bits, we cannot decode the sequence up to this point. Hence it is it is not an instantaneous code. For the next code sequence, suppose code sequence, we have a equal to 0, b equal to 1 0, c equal to 1 1 1 0, and d equal to 1 1 1. So obviously this is a singular code, right? Because for all of them, we have a different code word for each symbol. A has 0, B has 1 0. None of them overlap. So it is a singular code. Next, is it uniquely decodable? Yes. How? Because suppose we have a sequence, namely assume 0 1 0 1 1 1 1 0 1 1 1 here. So let's start with the first bit. The first bit here, it's a 0. So does any of the code words start with 0? Only A. Hence, the first bit will obviously be A because there is no other alternative, right? Then moving on, the next bit, it's 1. So we can't say anything about that, right? Because it can be B 1 0 or C 1 1 0 or D 1 1 1. So again, we move on, we get 1 0, right? So what is the only possible symbol for which the code word has 1 0? It's B again, right? So it will be B. Next, the code weight we get is 1. So it can be either B or C or D, right? Again, moving on, again, so we look at the next bit. The next bit also has 1. So it can be either C or D. So, and again, moving on, the next bit also is also 1. So what's the only possible code? Which does this code word refer to? It refers to D. So it will be a D. So looking again, we start from the next bit. It's 1, right? So it can be either B or C or D. So we look at the next bit. It's 0. So it can be only B. Similarly, we start again 1 1 1. It represents C. So you can see this is an uniquely decodable code, right? Because there is only one possible way in which you have decoded this sequence. So there is no other possible way. So this is sequence will be A, B, D, B, C. So hence it will be an uniquely decodable code. Next, moving, is it a instantaneous code? Yes, but you Lux, uh, how is it is an instantaneous code, right? Because we have to look at the next bit and again. But the instantaneous bit, it is an instantaneous code because we, after the completion of a single code word, we don't have to look at the next bit. For example, here, after we have seen 1 0, right? After we have seen 1 0, we don't need to know the next bit. We have received this bit 1 0, and we can deduce that it is B without knowing the next code word for that. Hence, it is a instantaneous code. Next, so the next discuss another code sequence. A is 0, B is 0 1, C is 0 1 1, D is 1 1 1. So here you have seen that it is singular code because all of the symbols have unique code words. Now, is it uniquely decodable? So let's see that with a sequence. 1 0 0 1 1 1 1 1. So let's look at this sequence. So for the first for we look at the first bit 0. So it can be A or B or C. Without looking at the next subsequent bits, we cannot tell for sure, right? So again, we move to the next bit. So it is 0, 1. So 0, 1. So it can be either B or C, 0, 1 or 0, 1, 1. So for that, for that purpose, we have to look at the next bit. The next bit is 0. So it cannot be C, 0, 1, 1, right? So it has to be B. So the first code word will be 0, 1. It will be B. So let's start with it again with the next bit. It is 0. So again, it can be either B or C, A, B or C. So we move to the subsequent bit. The subsequent bit is again 0. So there is no sequence here which has a prefix 0, 0, right? So it has to be A. So the third bit will represent A. So moving on, the fourth bit has 0. So again, it can be A or B or C. So just so then it can be A or B or C. So again, we have to look at the subsequent bit. It is 0, 1. So again, it can be B or it can be C, right? So we have to look at again the next bit. So it is 1. So the only possible code word for this will be 0, 1, 1, which will be C, right? That's the only possible way in which this can be decoded. So we'll have to so we get the next code word 0, 1, 1, which represents C. So we move to the next bit. It is 1. So it can be D. It has to be D actually, because the sequence is starting with 1 and there is no other possible code word for that. So it is D. So we get the sequence and we have decoded and we get B, A, C, D. So we can see that there is only one possible sequence which we can get from this. So hence it is so it is uniquely decodable. But is this instantaneous? No. Why is it not instantaneous? We can tell about we can just show that from the first two bits. First we had the 0. The first bit was 0, right? So for the first bit, it could the first bit it could represent A, but we were not sure that it was representing A until we without checking the second bit. So on checking the second bit, we got 1. So 0, 1, it could only represent B, right? Without knowing the subsequent bit, we could not have foretold whether it was A or B. Hence lies the dilemma. Hence it cannot be instantaneously decoded. Hence this is a non-instantaneous code. So yeah, that's basically regarding the code word. So is the PowerPoint slide visible?
How are you?
So next we move on to Huffman coding. So what is Huffman coding? So Huffman code is a coding scheme, right? To find the most efficient coding scheme for which is finite symbol sequences. So the number of symbols which are finite for this Huffman coding is applicable. But to apply Huffman coding, we have to know the probabilities beforehand before we use that. So there are different types of codes like adaptive Huffman and LZ codes. These are not really applicable. But first it is a prefix code, right? Do we have learned about prefix code? In a prefix code, no code word is a prefix of another code. Right here, A is a prefix of B because 0 is in 0, 1, right? In the beginning. So A is a prefix of B. Hence, this cannot be a prefix code. So this must not occur in a prefix code. So Huffman coding is a prefix code. Hence, it will be uniquely decodable as well as instantaneous. So we'll start with an example, so it will be easier to understand. Suppose there are 5 symbols which are which we can transmit, and these symbols are probability 0.4, S1 has 0.2, S2 has 0.2, S3 has 0.1, and S4 has 0.1. So, so how will we encode this? So first, we will use something called a Huffman tree. So, how is a Huffman tree used? So we'll first arrange the symbols in the decreasing order of probabilities. So S0, which has the highest probability, at 0.4, we will write it at the topmost, and the S4, which has at 0 has the lowest probability of 0.1, will write it at the bottommost level. So what will we do for the? Is my cursor visible?
Yes, Bhaiya, it is visible.
Yes, best.
Huh. So you can see for these two, right? S3 and S4. So so the for the bottommost two elements, so we will assign a 0 to suppose S3 or and 1 to S4, or we can also interchange them. We can write 1 at the top or 0 at the bottom. It's basically the same, right? And then we add these probabilities. So adding 0.1 plus 0.1, we get 0.2. So 0.2, where does it rank in the list of probabilities? It is equal, right, to the first the probabilities of S1 and S2. So it doesn't really matter where you place it. So here in this example, we have placed it at the topmost, because since all of these probabilities are same, it doesn't actually matter. Next, next we will look at the stage two. Again, the similar process is done. For the lowest two elements, we'll assign 0 at the top and 1 at the bottom, and we'll add these probabilities. So on adding them, we get 0.2 plus 0.2, which is 0.4. So we move it to the, so we can rank it at the top, since the first, since S0 has equal probability of 0.4, and the sum of these two is also 0.4. So we can place it anywhere. We could have placed it in the bottom also. The end result would have been same. And the end result would not have been same, but the length should be the same. That is the main condition, right? So again, for similarly for 0.2 and 0.4, we assign 0 and 1. Again, we move on to stage 4. So 0.4 plus 0.2, it has a probability of 0.6, right? So which is higher than 0.4. So it will be place it at the top, and 0.4 comes at the bottom. Again, we assign 0 and 1 to this. So this basically completes the Huffman tree. Now we have done this. So how will we actually find the code word for each element? So yes, so we will start with here. Suppose for symbol S1, S4, right? So we have to move along these arrows to find out the code word. So that's basically. So 0.1, we have assigned 1, in the code word 1, right? And on moving along the arrow, we reach stage 2. Here, no bit is being assigned to that. Again, moving on to stage 3, we say that along the arrow, we see that 1 is assigned to it again. And again, moving on along the arrow in the stage 4, a 0 is assigned to that. So what does it basically? We will start with stage 4. So it will be 0, and moving along the arrow, it will be 1, and again it will be 1. So S4 will have a code word 0, 1, 1. Similarly for S3, uh, S3, how is it? How does it move? It moves along. It ends with 0. Then again, it moves along this arrow. This arrow, it reaches 1, and in the next stage, it reaches 0. So it will write 0, 1, and 0. For similarly for symbol S2, in the stage 1, there is no bit assigned to it. In stage 2, bit 1 is assigned to it. In stage 3, again, no bit is assigned to it. In stage 4, bit 1 is assigned to it. So its bit will be starting from the uh, means newest state. Stage 4 is latest state, right? So stage 4, then stage 3, then stage 2, then stage 1. So while writing the code word, we'll start with the means latest state. So 1, moving along the arrows, 0, 1, sorry. So its code word will be 1 1. Similarly for S1, moving along these arrows, uh, we encounter the bit 0. And moving on to stage 2, there is no bit assigned on this stage. On its stage 4, 1 is assigned to it. So 1, 0. And similarly for stage 4, no error is taking place. We move along the same stage. In stage 2 also no bit is being assigned. In stage 3, 0 is assigned to it, and in stage 4, 0 is assigned to it again. So its code word will be 0 0. So this is basically Huffman tree. It's a bit difficult to explain it on this picture. We'll use as an example and show it on the whiteboard after the simulation, MATLAB simulation. So let me start my MATLAB file. Is MATLAB visible to you guys?
Yeah.
Okay, so we'll learn about modulation techniques in this simulation. So what is first is a binary phase shifting BPSK. It is a digital modulation technique. In this technique, we send different phases of the carrier for different values of the message signal. As it says in the name, binary phase shifting. So we shift the phase according to the different values of the input message. The carrier signal, we need a carrier signal, right? CT, which is A cos 2 pi CT. We'll change the phase in the carrier signal and so embed the message into this carrier signal for efficient transmission. So in BPSK binary phase shifting, we will send two phases of the carrier signal. It can be cos 2 pi FCT or 2 pi FCT plus pi. So there is a phase change of pi depending on the input. Suppose for 0, it has a phase of 0, and for 1, there is a phase shift of pi. So suppose we have a message signal M. All right, it is 0 1 0 0 1 1 1 0. So for easier application, we will change the zeros to 1. So M will be 2 times M minus 1. So what this basically does is multiply each element of M with 2 and subtract 1 from it. So 2 times 0 minus 1 is minus 1. Again, 2 times 1 minus 1 is 1. So the ones remain is 1 and the zeros change to minus 1. So now we have to change this message signal into an pulse. So we have, suppose we take the duration of the pulse to be 0.1 or 0.1 seconds. And so that is T basically. T is the duration of the pulse. Again, we have take another, we have another unit dt, which is TA by 500, suppose. So this is a sampling period. So sampling period. So sampling period is means we'll take the output of the message signal for at each interval. So the pulse duration is 0.1 seconds, and we are dividing it by 500. So we will take 500 samples during that pulse duration. So now T is another matrix which is represented in like this. So what does this syntax actually mean? So suppose we have a matrix A, which I'm just showing an example. 1, 2, suppose 86. Suppose 8. So what this will basically do? It is a matrix which starts from 1 and there is a subsequent difference of 2. Uh, there is a subsequent difference of 2 between each elements, and it will end at 9. So after 1, there is a difference of 2, and the next element will be 3, and then the next element will be plus 2, 5, then it will be 7, that it will be 9, and as it reaches 9, it will stop. So that's basically what this syntax is representing. Now TA is the pulse duration times size of m by 2. So as m is a matrix and 2 here it is used to represent the tells us which dimension we want to know. So here m has 8 bits, right? So it is an 1 cross 8 matrix. So size of m comma 2 tells us that we have to take the second dimension. So TA times 8. So that's what it's meaning. So we plot S, which is equal to ceiling of t by TA. So what does ceiling function? You know the ceiling function, right? So suppose we have and the ceiling function basically does that for 0.1 for any value of which is between x and suppose 1, it will become 1 for that. So that's basically the ceiling function. M of ceiling of t by ta. Now t here is a matrix, right? So as I've shown, so for each interval dt and it has a difference of dt, and it will continue up to ta times 8, right? So suppose the first element of t will be, what will be the first element of t? The first element of t will be dt, which is equal to ta by 500 as we have defined, right? So on what will on so dt by ta, so it will be 1 by 500, which is less than 1, right? So what will the ceiling function do? It will convert it to 1. So s, the first element of s will be equal to m of 1. So it is, which is basically the first bit, which will be 0. Similarly, for the second element of s, what will be the second element of s? The second element of s will be twice of dt, right? Because as I had shown in the example matrix, how this is done. So the first element is dt, and there is a difference of dt. So the second element will be twice of dt. So again, on and dividing the scaling function, twice of dt divided by a, it will again be 2 by 500, which will again be less than 1. So again, the second element of s will also show m of ceiling of something less than 1, which will be equal to m of again 1, right? So this is actually what is being done through the sampling period. There are 500 samples being taken for each message. So on plotting this, we'll get this plot. Here, as you can see from for the pulse duration 0 to 0.1, its value is -1 because the message signal is 0, and we have converted all zeros to -1 actually. So this is the plot for, and during the second from 0.1 to 0.2, the message has a value of 1. So its value will be 1. This is basically the plotting of S. Now we define the FC, which is the carrier frequency, or the frequency of the carrier signal, which we have shown here. This carrier signal will change the phase of this carrier signal to transmit the message actually. So now we'll modulate this. So to modulate this, we'll multiply each element of S with cos 2 pi fct. So what does dot dot uh, dot times product. This basically multiplies each element of a matrix. Uh, so these are two matrices basically, right? Because T is also a matrix and S is also a matrix which we have shown here. So suppose so it will multiply. Suppose we have a matrix 1, 2, and the dot multiply it with 3, 4. So output will be basically 1 times 3, 2 times 4, which will be equal to 3. 8. So that's basically being done by this modulation. This is a modulated signal. So suppose this modulated signal, we have transmitted this modulated signal, but it will not be transmitted without some disturbances, right? So we add additive white Gaussian noise to it. What is AWGN? This AWGN is basically a noise model which is used to simulate the disturbances which can appear on the signal while it is being transmitted. So it is basically a model for simulating the environment and the disturbances which can occur while the signal is being transmitted. So for again demodulation, for demodulation, we'll multiply the received signal with modulate with C, which is cos 2 pi ft. So we'll so what will be the basic, and then we'll apply the convolution. So we have learned in signals and systems, right? The convolution, how it is done. So we'll convolve this demodulated signal with dt times 1 of ta by dt, comma same. So what does this syntax mean? So the first two elements here, dmod and dt, these are the signals which we have to modulate. And this same function actually takes the central part of the modulation. Suppose we have taken conv u comma v as it is shown here. So then we'd have received the output which would have been of the size of u plus size of v minus 1. But when we give the shape, when we give the syntax same, it will give us a convolution of the size of u. So that's basic, and which is done by taking the central part of the convolution. So that's basically what's being done. And then plotting this convolution, so we get a plot something like this, right? So as you can see, this output is not very clear. So we have to apply some threshold. Suppose for all those values which is less than 0, we'll change them. Which is less than 0, we'll change them to 0, and for change them to -1. And for those values which is greater than 0, we'll change them to 1. So on plotting that, we get something like this plot similar to this one. So now we have to take these samples, right? So this is the signal which you have received. Now to extract the original message which you have transmitted, we have to extract the signal. So we'll have to take samples. So for what will be the best way to take samples? To take the values at the middle of each TA. And what is TA? It is the pulse duration, right? So it has a pulse duration, and the pulse duration was 0.1. So we'll take values at at the mid 0.1 by 2, which is basically 0.05. And again, we'll take the next pulse duration at 0.15. So that's basically what the syntax is showing. So sampling times will be 0.05, 0.15, 0.25, something like that. So then we take so to reconstruct the message, we take the S of the values of the values of the signal which we have received and demodulated and such, and threshold, that applied threshold at this instant is 0.05, 0.15, and we get the reconstructed messages minus 1, 1, minus 1, minus 1, 1, 1, 1, 1. So if you remember that in the original message we have assigned minus 1 to 0, and 1 has been was same as 1. So again we applied this simple threshold, suppose, and we get the values and reconstructed as 0, 1, 0, 0, 1, 1, 1. So this is basically the original message signal which we had transmitted. So you can see we have first we have the message signal, we are converting the zeros to minus ones. So then we are taking samples at 500 times in each pulse duration. Then we are plotting those. Then we are modulating it with cos 2 pi epsilon t. Then we are adding white Gaussian noise to simulate the disturbances. Then we are demodulating it again, and we are applying a threshold, and then we are taking a sample at the middle of each pulse duration to get the to extract the original message. So this is basically binary phase shifting. So now quadrature amplitude multiplexing. So what is QAM? QAM basically means we are transmitting two different signals using a single carrier message. So how this is done? The first signal is multiplied with a sine carrier, and the second signal is multiplied with a cosine carrier. So it's the same process actually. There's nothing different with it, but so we have two messages, M1 and M2. The first signal is multiplied with a sine carrier actually, sine 2 5 ct, and the second is done with a cosine carrier. And if subsequent modulation and demodulation is done using using the respective sines and cosines. So here FC has a frequency of 10 kilohertz, 1E4. So E4 is basically represents, you might have seen this in calculators. So 1E4 is represent 10 raised to the power 4. So 10,000 kilohertz. And the pulse duration TA, it is 1 e raised to the power minus 3, which is 10 raised to the power minus 3, which is 0.1 milliseconds. So number of samples in 1 pulse, NS. So the sampling period dt is TA by NS. So 1,000 samples will be done for 1 pulse. Since TA is the pulse duration, suppose the message first bit message lasts for TA seconds, and when we are dividing TA by NS, so we'll be taking 1,000 samples during that pulse duration of a single bit. So do we have two message signals, M1 and M2? So these are the message signals. Then again, we're converting the zeros to minus ones as in the first BPSK model. Then we are taking the same matrix as below for the sampling period. Then again, we are taking two message signals, ceiling of T by TA, S1 and S2. We are plotting them and we get this message signal. Then we are the first message signal we are modulating with the cosine, and this for the second message signal we are modulating with sine. So that's basically the difference, as you can see here. The rest of the parts you can carry on as if it was a BPSK signal, but here one signal we are modulating with the cosine, the second signal we are modulating with the sine function, and then we add this to get the final modulated signal which will be transmitted. Now we are adding some noise, white noise to it of 10 decibel. So AWGN does that. And then again, to extract signal 1, we are multiplying the modulated signal with cos 2 pi ct, and signal 2 to receive the signal, extract the signal 2 which is related to the part which is modulated with sine. We are again multiplying it with this sine function. So then we are applying the convolution similar to the above. Similarly, we are applying the convolution again, and on plotting that we get plots like this. Again, we have, if we apply the threshold and plot them, we get these plots, and on sampling them again in the middle of the pulse duration, TA by 2, and we can reconstruct this as shown below, M1. We will get the original M1 message. So it's basically the same as BPSK, at least in the while simulating it in MATLAB. But what we are basically changing is uh, the with the carrier. It's a carrier signal. So we are multiplying the first message with the cosine, the second message with the sine, similar to that. So that's the basically different basic difference. Rest of the part he says is same coding as below. Next we come to QPSK, quadrature phase shift keying. So binary use two phases. So quadrature 4. So how does it use 4 phases? Suppose we have a signal message 00011011. So in QPSK, we'll take 2 bits at one time and transmit a single phase for a single pulse duration, particular phase. So what's basically the advantage? We are transmitting 2 bits using a single phase, right? So less time is required, and less time is required, and we can send double the bits at for the same duration. So suppose we have assigned for 00, we'll send it at the base phase 5. For 01, we'll send it at a phase 5 plus 90. Similarly, for 10, we'll send it at a phase 5 plus 180. For 11, we'll send it at a phase 5 plus 270. So one easy way to describe this modulation scheme is that we take the even bits and the odd bits separately, and we'll double their duration. Suppose this is the message signal 00011011. We'll take the even bits out here. ME is the even bits, which will be 0101, and the odd bits will be 011 and 1. So this will be the even bits, and these are the odd bits of the message signal. So again, we are converting it like the previous two, for the previous two modulation schemes. We're converting the zeros to -1. So ME will be -1, 1, -1, 1, and MO will be -1, -1, 1, 1. So the modulated signal will be ME cos 2 pi fct plus M of odd times sin 2 pi fct. Similarly to the QAM. So here in this case, phi is the phase which is transmitted, and 00 is transmitted. That is effectively -1, -1. Right. So -1, -1. So ME is -1 and MO is also -1. So what will we get as the modulated signal? Minus cos 2 pi fct minus sin 2 pi fct. So you know how to do this, right? On multiplying and dividing by √2. So we'll get minus of square root of 2 cos 2 pi fct plus 45 degree, right? Because half is equal to 45. So which will be equal to cos 2 pi fct plus 135 degree on using the taking out the negative sign. So this is why are you using QPSK? Because it reduces the data rate, right? We are transmitting twice the data for at the same time, right? But if there is an error or something like that, so yeah, so its error is also increase, hence the bit error rate is also increases. So how will you implement it? Suppose we have a message signal 0001100110. So again, we're converting the zeros to ones. So we are assigning the even bits to ME and the odd bits to MO. So the rest of the code, it is the same as quadrature amplitude modulation. So the phase duration is 10 raised to the power minus 3, which is 0.1 milliseconds. The sampling rate ns is 500. So for the pulse duration, TA will be sampling the signal 500 times. So dt, which will be TA by ns, which will be sampling time. So again, we are taking the matrix which represents the instant stage in which the signal will be sampled. So first it will be sampled at dt, then it will be twice at dt, and so on till it reaches TA times size of the message, even message signal. So we'll take the S1 and S2, which is similar to the quadrature amplitude modulation of M1 and M2, right? So on plotting these things, then we are first the cosine, we are multiplying it with the cosine component, and for the we are multiplying the odd signal with the sine component, and when adding them, we'll get the modulated signal. Now, on moving on to the demodulation part. The demodulation part we have received this the received signal. We have added some white Gaussian noise to it. Now, the signal for extracting signal 1, we have to multiply it again with the modulated signal with cos 2 pi ct. For the signal 2, which will be multiplying it by sine 2 pi ct to find out this part. Similarly to that. Now again, we are convolution. We take the convolution or apply the convolution filter, like similar to the case in quadrature amplitude modulation. Right here we have applied the convolution filter to find out the first message signal and the second message signal. Similarly, there's the same thing is being done here. So and again we apply the threshold to find out if a signal is 0 or 1. Then we are taking the sampling times at the midst of the phases. Then we are reconstructing it by taking the values at those times. So we get M1 and M2. So this M1, what does M1? M1 signifies the even part, right? And M2 signifies the odd parts. So to get the original message signal, we have to combine them. So what we are doing basically, M reconstructed, that is the final message, is shown as M2 reconstructed, M1 reconstructed. So what is basically M2 here? 0, 0, 1, 0, 1, and M1 is 0, 1, 0, 1, 0. So it is a 2 cross-ride matrix. So what does this function do? This function will convert it into a matrix similar to the form 0, 0, 0, 1, 1, 0, 0, 1, 1, 0. It's transpose actually. So this function converts it into an 10 cross 1 matrix. So we are again taking the transpose to get this. So transpose of a transpose function will be original, right? So this is what we'll receive at that time as M final. So this is the original message signal. So that's basically the modulation and demodulation techniques which you can do in MATLAB, simulate using MATLAB. We'll send you this file and also the Word file, so you can practice it in Octave also. You can try changing these parameters and plot them to find out how they are. So what these things are doing, the pulse duration, or changing the pulse duration, or changing the sampling rate. What changes are being occurred. You can change these variables and you can see how the signals are changed. You can plot the modulated and demodulated signal also. Yeah, so that's basically what this workshop was in this workshop for today. So, any questions? If not, then we can conclude, I think, Dinesh.
Yeah, sure. I mean, if anyone
Yes,
has any doubts, yeah. Otherwise,
you can ask in the group also if you have any doubts. You can, and also please register if you have not done till now. We'll be in next and probably with the last workshop, we'll be discussing a sample PS and how you can solve this, how you approach the problem. So that will basically be discussed in the last workshop. Yeah. So that's
next
basically
workshop for
it.
Commnet will be after mid semester. So in that we will be discussing the sample piece.
Okay, if anyone, no one has any questions, we can conclude, I think.